The topic of our presentation is master-slave flip-flop. So we already know that we have four different types of flip-flops. We have our JK flip-flop, SR flip-flop, D flip-flop, and T flip-flop. Now, even after having these four types, why do we need master-slave flip-flop is what we need to know first. That is, what is the need to have this master-slave flip-flop? So as we all know that in JK flip-flop, whenever my input J is equal to 1 and K is also equal to 1, and when the clock whatever is given to it is 1 or it is high for a very long period of time, then the output Q that comes out of it will toggle as long as the clock is high. So which makes Q to be very unstable. So this problem whatever is faced with JK is called as the race around. So in order to overcome this drawback of JK, which is called as race around, it can be overcome by making sure that the clock is at logic 1 only for a very short period of time. And this can be done by making use of master-slave flip-flop. So another way of overcoming this drawback of JK is by using edge-triggered flip-flops. So when I talk about the edge-triggered, it can either be positive edge or it can be the negative edge. So that is the reason why we make use of master slaves. So now let's look into what exactly is a master slave flip-flop. So in a master slave flip-flop, we will be having two flip-flops where the first is called as a master and the second flip-flop will be called as the slave. Now the clock pulse whatever is given to the master, the inverted clock pulse of that is what goes to the slave as shown in the figure. Now apart from that, the output that comes out of the master as it's shown over here in the figure, that is Y, is given as the input to the slave. So this is how the master and slave works. So whenever the master is going to receive a clock pulse of 1, at the same instant of time, the clock pulse that goes to the slave will be 0, which means that at a particular instant of time, a master is going to be active, but the slave will remain inactive. And in the other case, when the clock pulse that goes to the master is 0, which means that the master is going to be inactive, at that same instant of time, the clock pulse that goes to the slave will be 1, which means that the slave will be active. So at a given point of time, it's either the master or the slave that will be active and not both. Okay, so this is the logic diagram of it. It is the logic diagram of SR master slave as shown in the figure. And this is a circuit diagram. So the previous slide we were showing you the block diagram, and this is what is present inside the block. We have represented it by making use of only NAND gates. So the previous slide was showing you the SR master slave. This is the circuit diagram for JK master slave, where we are showing you what is present inside the block. So in the case of JK, one thing we have to notice is that the output, whatever comes out of the slave, is given back to the master as its inputs as shown in the figure. This is the only difference that we can find over here. And this is the timing diagram of it. So the working of it is something that I'll be talking about. So here we can see that whenever my clock pulse will be 1, that is whenever it is high, the clock pulse that goes to the master is 1, but the clock pulse that is given to the slave will be 0, which means that whenever my clock pulse is 1, it is only the master that is going to be active and the slave will not be active, which means that irrespective of whatever is the value of S or R, whatever is going to the slave or whatever is a S and R values which comes to the master, there will be no effect to the slave because it is not going to be active. Right, so now whenever my clock pulse is high or whenever it is 1 and when my S is 1, which means that it is going to be set. But what will be set is only the master which will be set. So the output that comes out of the master, which we have taken as Y, and Q is the output that comes out of the slave. So only the output that comes out of the master, which is Y, will be set to 1 during the positive edge of the clock pulse. And as it's shown in the figure, there is no effect on the output that comes out of the slave. It is given as 0 itself. Now during the negative half cycle or during the negative edge of the clock pulse, that is exactly when the slave output will change. Okay, because that is when the slave will be active and the master will become inactive. So we can see that during the negative edge, even though the S value is dropping down to 0, it will have no effect on the output that is coming out of the master, because the master will remain inactive during the negative edge and it's only the slave that is active. And the slave is going to follow the master as shown in the diagram. So that's how it's going to get its name called as slave. So that's why it's called as master slave, because the output of the slave is going to follow the output of the master. But this following is going to happen only after 1/2 clock pulse. That's because it's during the positive edge that the output of the master changes, and it's during the negative edge, that is after 1/2 clock pulse, that the output of the slave will change. So now we have various types of master slave flip-flops that we have. We can have master slaves in all the cases. That is, we can have master slave SR flip-flop, we can have master slave JK flip-flop, we can have master slave D flip-flop, and we can also have master slave T flip-flop. So in this presentation, we will be concentrating more on master slave D flip-flop because our real-time application is based on master slave D flip-flop. And we will also be looking into master slave JK flip-flop as well. Now, master slave SR and T will be working almost similar to that of the normal working of master slaves. So if we know the truth table of SR, JK, D and T, one thing that we must remember is that this will work, or it is going to follow its truth table as long as the clock input is going to be 1. But when the clock input given to it is 0, it will have no effect on the master, which means that the output, whatever comes out of the slave, will be retaining its previous state. So this is about master slave JK flip-flop. So here the only thing is that we have replaced the two flip-flops with JK. And as I've already told you that the output of the slave is fed back as the input to the master. That's the only difference that we can find. And apart from that, the clock, whatever is given, the clock pulse given to the master, the inverted clock pulse of that is given to the slave. Okay, and this is the timing diagram of my master slave JK. So as we already know what is the working of master slave, so it's going to work just the same. So we know the truth table of JK, that is whenever my J and K values both are going to be 0, it is going to retain its previous state, and when J is 1 and K is 0, it is going to be set. When J is 0 and K is 1, it is going to be reset, and when J and K both are high, it is going to toggle. Now in the first case, when my clock is going to be 1, or during the positive edge, if I would take edge triggered master slave, then during the positive edge, we have J to be 1 and K to be 0. So now when J is equal to 1, it means that it has to set. But it's only the output that comes out of the master which will be set, and not the output that comes out of the slave, because we know whenever the master is active, the slave will remain inactive. So as it's shown in the diagram, it's only QM, that is the output coming out of the master, which will be set to 1, and it will have no effect on Q, which is the output that comes out of the slave. So it is retaining its previous state. So the previous or the initial state of Q is 0. So it will have no change and it will still remain to be in 0 itself. Now during the negative half cycle or during the negative edge of the clock pulse, J still remain to be 1 and K is 0. Now during this negative half cycle or during the negative edge, the master will be inactive. So even though even though J is going to be 1 and K is going to be 0, it will have no effect on the output that will come out of the master. So it's only the output of the slave which is going to be set to 1 during the negative edge of the clock pulse. So this is what is going to happen. So we can just look into the diagram and we can find out how exactly the QM and Q changes. So from it, we can also know that the output of the slave is just following the output of the master, but the only difference is that QM changes during the positive edge and Q is going to change during the negative edge of it. Now, when I'm talking about master slaves, so this master slave, we can have two different types of it. We can have level triggered or we can also have edge triggered. So level triggered means during the positive and the negative half cycles, and edge means during the positive edge and the negative edge of the clock pulse. So that's the thing. Now this is the master slave D flip-flop. So over here, the only difference is that instead of using JK flip-flops, we have replaced it with two D flip-flops. And the same thing, the first is called as the master D and the other flip-flop is called as the slave D flip-flop. And we have the clock pulse that is given to the master and the inverted clock pulse that is coming out to the slave. And this is the timing diagram of how it works. So it's just the same. So we know the truth table of D, that is the output will follow the input given to it. So whenever my input is going to be 0, then the output that comes out of it will also be 0. And whenever the input given to it is 1, then the output that comes out of it will be 1. So that is known to us. So looking at the timing diagram, during the positive edge, D will remain to be 0. Now QM, that is during the positive edge, only the master is going to be active. So your QM is going to become 0. Now since the initial state of Q, that is the output of the slave, is 1, it would still remain to be 1 itself because it's going to be inactive. So it will have no effect on its output. Similarly, during the negative edge, we can see that my D is 1. So even though D is 1, QM will still remain to be in 0 or in its previous state because during the negative edge, QM or the master is going to be inactive. Right, so during the negative edge, now my Q is going to set to 0 because it has to follow the output of the master. Now, one more thing that I would want to tell is it's during the positive edge that the value of QM will change. Okay, and that time the data or the information is not passed from the master to the slave because the slave is going to be inactive. Now, during the negative edge is when the information or data is being passed from the master to the slave. Now, this is the truth table of it. So here we can see that it is the same truth table of the D flip-flop itself. But for master D flip-flop, we can see that it is following its truth table only when the clock is high. That is, only when my clock is 1 will the input 0 give Q to be 0. And when my D is 1, my Q is going to be 1. But whenever my clock is 0, that is when my clock is low, it is going to retain back its previous state. There will be no effect because the master itself was going to be inactive. And this is the diagram of D-type positive edge master slave flip-flop. So I've shown it over here because my real-time application is based upon positive edge D-type master slave flip-flop. So this is the internal diagram of it. We have shown it only by using NAND gates. Now when I talk about flip-flop, so flip-flop as it tells, so flip-flop is nothing but it is a bistable device, which means that it has two stable states and it can store one bit of information. So as flip-flops are itself used to store information or store data, it is it's used in memory elements, it's used in shift registers, it's used in counters, it's used in frequency dividers, it's used in bounce elimination switches. So flip-flops will find its uses in various applications, and in our day-to-day lives itself, we can find it to be used in many appliances and in many cases. So those were some of the general applications of it. Now, since our topic is master-slave flip-flop, so I would be talking about one real-time application of master-slave flip-flop. So I have taken up a positive edge-triggered master-slave D flip-flop, and this will be used in interface circuits. So we will look into how this is used in interface circuits. So before we go on to that, we first need to know what is an interface circuit. So an input-output interface will consist of the circuitry which is required to connect the input-output device to the processor. So now this interface will be having two sides. So on one side it is going to be connected to the hardware, and on the other side it will be connected to the processor. And it is over here that there will be some transfer of information between the interface and the processor. So on this side, wherever there will be transfer of information between the processor as well as the interface is what is called as the port. So now we have two different types of ports. We will be having serial ports and we will have parallel ports. So in this presentation, we will be concentrating on only parallel ports. So when I talk about parallel ports, we have 8-bit parallel port. So in parallel port, we will have 8-bit input port and we will have 8-bit output port. So here we will be concentrating on only 8-bit input port, and even the output port will be just the same as the input port. So this is how the connection will look on the input side. So here, as it's shown in the diagram, we will be having the interface, which is called as the input interface. And on one side of it, it is connected to the keyboard, which is nothing but our input device. And on the other side of it, it is going to be connected to the processor. Okay, so usually a typical keyboard will consist of many mechanical switches, which will usually be in open state. So whenever we are going to press a key, that is when one of the switch will get closed. So when the switch closes, it means that there is transfer of data or information from the keyboard to the encoder circuit. Now the work of the encoder circuit is that it's going to encode the information that it has received from the keyboard. Now it's going to send the encoded data or the ASCII value to the input interface. But along with that, it also has a valid line which is being sent from the encoder circuit to the input interface. Now what is the work of valid line? So valid line is going to tell the input interface that a valid information was being passed from the keyboard to the input interface. Now, whenever this data is being transferred from the encoder circuit to the input interface, that data is being stored in the register called as data N. So, data N will now be storing the information that was passed on to it. Now, inside the input interface, we have one more thing called as status flag. Here it's called as SN. So since it's input port, so therefore it's called as SN. In the case of output port, the name of the status flag used over there is SOUT. So in this presentation, we will be more interested to know what is present inside the status flag, because it is there where we will be making use of our master-slave D flip-flop. Now what is the work of status flag? So here the status flag is going to be turned to 1 whenever the information is being stored in data N. And whenever the data N information is passed on to the processor, that is when now the data N is available to receive much more information from the keyboard. So that is when the SN will be turned to 0, or it will be cleared to 0. But during the process, whenever the information is being transferred from the input interface to the processor, during that process, the SN flag should still be 1, because data N is still not ready to receive information from the keyboard. So therefore only when the processor will send the master ready, only then will the SN will be cleared to 0, and only then will data N be ready to receive information from the keyboard. Now on the other side of the input interface, which is connected to the processor, we have data line, we have address line, and we also have one more line called as read or write. This is going to tell as to what sort of operation must be performed, whether read operation should be performed or write operation. And we also have master ready and slave ready lines. So this is about the input connection of it. And this is the circuitry, whatever is present inside the input interface. As it's shown, we have the data that is coming from the keyboard, which is being stored in the data register called as data N. And to it, we also have a valid line, which is telling whether the information received is valid or not. And we have status flag present inside the interface, which tells whether the data N is ready to receive information or whether it already has data present inside it. And that information, whatever is passed on, will be passed to the processor for further processing. And this is the circuit diagram, or what is present inside the status flag, because this is exactly where we make use of our positive edge triggered master slave D flip-flop. So as it's shown in the diagram, so whenever my valid is going to be high, that is whenever my valid will be 1, that is whenever it is going to tell the interface that a valid information was being passed from the keyboard, that is when my D flip-flop, my master slave D flip-flop will be set to 1. Now whenever my master slave D flip-flop is going to be set to 1, it is going to change the state of the NOR latch, whatever is present, which will change the state of SN. Then the SN will be set to 1. Now, the state of this latch must not change while Sn is being read by the processor, because during the process of transfer of information between the data in and the processor, the data in is still not ready to receive information. So therefore, Sn should be still 1. Now, this state of the latch must not change while Sn is being read by the processor. So hence, the circuit ensures that the Sn can be set only while master ready will be equal to 0. So both the flip-flop and the latch are reset to 0 when read data is set to 1 to read the data in register. So since the working of the status flag, whatever is present inside the interface, it is present both in input as well as the output interface. But in the case of output interface, it is S out, whatever is present, but its internal circuit diagram will be same as S in. Now this is the output connection. So over here what happens is data is transferred from the processor to the hardware component, whatever is present. Over here we are going to have the printer, which is the output device. So it is the data being transferred from the processor to the printer. But in the case of input connection, we've seen that data was being read from the keyboard and it was passed on to the processor. But in both the cases, we will be having an interface that will be connecting the hardware components with the processor. And this is the combined input-output interface, and this is the circuitry which is present inside it. We have both SN and SOut, which is our status flags, and along with that we have our data registers. We have data in and data out, and we also have the address decoders, and this is how it looks inside the interface circuits. So it is inside these status flags that we have our positive edge triggered master slave D flip-flop. So in this presentation, we have seen what exactly is master-slave flip-flop. Why is it used? We have seen about the 4 different types of master-slaves that we have. We have spoken in detail about JK, master-slave, D master-slave, and we also saw about some of the applications of the master-slaves that we have. And we took up one application, which was the application of master slave positive edge trigger D flip-flop in our input output interfaces. So hopefully it was very clear and it was useful to all of you. Thank you so much.